In this video, I will summarize what we learned about one-dimensional flows. So we considered autonomous one-dimensional flow, which is described like this: x dot equals to f of x. So x is variable, which describes kind of physical system or dynamical system. So it should be a real number. Function f have continuous first derivative at least on domain of definition. And for this system, what we found that solutions x of t, so it has family of solutions depending on initial conditions, and they have two properties. First property, they don't cross each other, which means that if x1 at t naught is not equal to x2 at t naught, then x1 at t is not equal to x2 at t for any time t. Yeah, so this is first property. And second property, solutions are monotonic. And these two properties make it very easy to analyze dynamics in this flow. So to analyze dynamics, what we do, we find first fixed or stationary solutions or equilibria, which are roots of algebraic equation. And then next what we do, analyze stability of equilibrium. So this means that if x is a root of f of x equal to 0, derivative of f when x equals to x capital defines stability of x capital. So if derivative is positive, x capital is unstable equilibrium, and if derivative of f is negative, then it's stable. And then therefore we can identify domains of attractions for all stable equilibria, and generally we can conclude on dynamics in the system depending on initial conditions. Next part of story is more challenging, is flows with parameters. So we considered flow with one parameter only, still autonomous, and we have parameter c. And now, so this function should have both first partial derivatives should be continuous. So let's put it like this. And x is a real number, and say parameter is also a real number. Okay, and then what we concluded? We concluded that number and stability of equilibrium depend on parameter. On value of parameter C. And therefore, from here we decided that there are important values of parameter C such that there is a number or stability pattern of equilibria changing. And these are called bifurcation values of C. Bifurcation values of parameter C. It's when A is a number or stability of equilibria is changing. So I formulated this using concept of structural stability, topological equivalence. And structural stability of flow. So this is, at least in explanation of what is K point when we have parameter. And then we considered so-called local bifurcations. So local bifurcations are bifurcations associated with separated, isolated, equilibrium. Then what we found, we found that bifurcations are bifurcation points. It is points, so bifurcation point. Which is given by value of variable and value of parameter, where bifurcation takes place. So this is a place where is a equilibria appear or disappear, or it's where their stability is changing. And we found that bifurcation points can only bifurcations can take place only at hyperbolic equilibrium. That is at, say, point x star, c star, such that f at x star, c star equals to 0, and derivative of f over x at x star, c star is also 0. And we identified 3 types of local bifurcation. 3 types of local bifurcation. So first is called fault bifurcation, and condition for this is like this. If at x star c star we have hyperbolic equilibrium, so this is pretty much for all three cases, so I will say one here, and mixed derivative, sorry, second derivative over x at x star c star is not zero, and first derivative over c at x star c star is not zero, then we have fault bifurcation. So when we have fault bifurcation, it is a place where two equilibria appear. What is appear? Of which one is stable and another is unstable. So if these conditions are broken, namely if first derivative over c is zero and second derivative over x is not zero and mixed derivative, so mixed second derivative at hyperbolic equilibrium is also not zero, then we have so-called transcritical bifurcation. So here what we have, two equilibrium here collide at this bifurcation point and swap stability. So this is signature of transcritical bifurcation. And next one, third type of bifurcation, which is called pitchfork. So for pitchfork bifurcation, derivative over c should be zero, second derivative over x should be zero, but mixed second derivative is not zero, and third derivative over x is not zero. So this is when we have pitchfork bifurcation. And signature here, one equilibrium is changing stability, and two other equilibria appear or disappear. The bifurcation point, at bifurcation point. And furthermore, when two other equilibria which appear or disappear, they have same stability, and their stability opposing the stability of the one which always exists. So if, okay, well, one example is like this. It was stable equilibria, then it became unstable, and two new appeared, and they both are stable. So let's put it like this. This is parameter C. This is x variable x, and this is bifurcation diagram in this case. And if two new equilibria which appear or disappear are stable, if these two equilibria are stable, then we have supercritical pitchfork bifurcation. Otherwise, if they are unstable, we have subcritical pitchfork. Okay, this is about three types of bifurcations. Then two more statements. No other local bifurcations exist. Particularly what it means that we remember when we were considering map, we had so-called flip bifurcations. So flip bifurcations don't exist in flows. No flip bifurcations in flows. And if these conditions, for example, if conditions for transcritical or pitchfork bifurcations are broken, then we still can have bifurcations, but these bifurcations anyway will be one of these three kinds, either fault or. So what it means, even this condition is broken, even these two conditions are broken, but other conditions for transcritical and pitchfork also broken, we go to higher order approximations, and we can end up with, for example, fault bifurcation again. And same is about transcritical and pitchfork. So we need, every time these conditions are broken, we get up to higher order approximations, but with these higher order approximations, if we get any bifurcations, they will be one of these three kinds. Okay. Bifurcations found in higher order approximations can be of one of these three kinds. Okay, and then I had to mention you, or I mentioned earlier, at least in one of my lectures, I have spoken about one important example for transcritical bifurcation, and now I will repeat it. So, important examples. If in this flow, in this, what we have, f of x c can be represented as x times another function of x and c, and g at 0, 0 is 0, then at 0, 0 we have transcritical bifurcation. So, well, it is easy to see that if in this case from here we conclude that f at 0, 0 is 0 and f prime over x at 0, 0 is also 0. So this 0, 0 will be hyperbolic, and if g is good enough, then two other derivatives, second derivative over x and mixed derivative over x and c, if they are non-zero, then we will have transcritical bifurcation. But this is satisfied in these conditions. And so this was first example. And second example, so again we consider x dot equals to f of xc, and if f of xc is odd function of x, then 0 is a place where we have pitchfork bifurcation. This is odd function of x, and I will add and derivative of f over x at 0, 0, 0. So this extra condition. So we have two conditions here. And first derivative over x is 0. Then at 0, 0 we will have pitchfork bifurcation. So by the way, I made quite a few corrections. In my lecture note, uploaded new version. You can look at it. But when I was correcting it, I found a bit nicer way to prove part of what is shown there. So in my lecture notes, I talk about derivative of over x, which first derivative is even function, second derivative is odd function, and this may look confusing. So another way to be easier is like this. If f of x is odd function of x, then its Taylor expansion to x should have only terms containing x to the odd powers. So, okay, this is f at 0, say c, plus derivative of f over x at 0 c times x, plus half of second derivative x at 0 c times x squared, and say plus 1 over 6 set derivative over x 0 c times x cubed. And since f of x is odd function with respect to x, this should disappear and this should disappear. And then we can further extend it. Now derivative of f over x can be represented as derivative of f over x at 0, 0 plus derivative of f over xc at 0, 0 times c plus second derivative. So here's second derivative, set derivative x c c at 0, 0 So here half c squared, and all of this multiplied by x. And so this way we got now third order approximation. So we got all terms up to third order approximation, and here we have one extra term of third order 0c times x cube. Now, according to this condition, we can remove this. And what we got is derivative, second mixed derivative. So what we will call this was called before, it was called, in my notes, I think it was called A3. So this was A4 and this was A5. So therefore what we have is A3 times x times c plus A4 times xc squared plus A5 times x cubed. And now we can see that this term is this term roughly multiplied by c, and since c for this kind of approximations is considered to be very small, xc squared, I can put here, xc squared much smaller than xc. And therefore we can remove this term. And after this, what we get is a3xc plus a5x cubed. And this is exactly what we considered to cause pitchfork bifurcation. If a3 and a5 are non-zero, then we have pitchfork bifurcation. So this is, well, anyway, so this was another important example. And here, maybe final comment. Okay, so I wanted to stop. Let's make final comment to find bifurcation points. For this flow, x dot equal to f of xc, you find roots for algebraic system. F of xc equal to 0, derivative of f of xc equal to 0. So roots hyperbolic equilibrium. And then at this place, let's say x star, c star, then you check derivatives f prime over c at x star, c star, second derivative over x at x star, c star. And if they both non-zero, then we have fault bifurcation. If first one is 0, then you will check this second derivative. At x star, c star. And if this non-zeros, well, you just compare with conditions for all three bifurcations, and so on. So this is idea, and I have illustrated this on an example, which I presented last Wednesday on online session. So it was recorded, and record can be found. Well, I placed the record on Vital. Goodbye.